Hello and welcome to this next lecture on fundamentals of acoustics. Today we are going to look at waves on a string. It is a continuous system, and for the first time we will actually see the derivation of a wave equation in one dimensions. The acoustic wave equation in one dimensions is exactly the same, so we will get a visual idea of what a wave equation looks like. So let us start. Waves on a string. A typical example would be strings on a musical instrument. When a musical instrument with strings is plucked, the strings carry vibrations or waves. And we are going to derive a model for that. Now there are a certain set of assumptions, okay. The first of these assumptions is that the string is under uniform tension. Okay. The second assumption is that the string has uniform mass density. Now since the string is a one dimensional structure, we will talk of mass per unit length, okay. That will be the linear density. Third assumption is that there is no damping in the string material. There is no dissipation whatsoever, okay. In the model there is no dissipation whatsoever. Number 4, the tension in the string is high enough that gravity can be neglected. The fifth is an important assumption. The string has no bending stiffness. This may need a bit of an explanation here. Normally if we have a beam, okay, and I apply a moment, then the beam bends such that the top fiber extends and the lower fibers contract. They contract. and in between there is a neutral surface which has not undergone any extension. Now, and the remaining portion of the beam from which this section was cut applies a resistive moment. Okay. Now, in the case of the string, when we mean there is no bending stiffness, what we mean is that there is no resisting moment that comes. The entire resistance, if there was a string originally and I apply a force over here, then the force deforms the string. Now, the resistance to this force comes through the components of the tension in the vertical direction. So, there is tension in this string, tension in this portion of the string, and then what they do is, as the string takes a deformed shape, now you have an angle and a component of the tension in the vertical direction, and that resists the force that is applied. That is what we mean by the string has no bending stiffness. And the last assumption, which is important, is that when the string takes the deformed shape or when it carries the waves, if this is my y deflection and this is my x, del y by del x is much less than 1. Okay. So, these theta values, the values of the slope are very, very small, such that we will make sin theta equal to theta. We will use this approximation. Okay. Now, here is a section of the string. This is the tension T at the right hand end, this is the tension T on the left hand end. This is the angle theta. This here is the angle theta. This is my x location, this is x plus dx. This is the vertical deflection y at x, and this is the, let us say, deflection at y x plus dx. Okay. Then this becomes theta x at x plus dx, and this becomes theta at x, and this is the uniform tension T, Okay. Now, the idea is to find the net vertical force. The net vertical force. The net vertical force, first of all, the force at the left hand end, force at x. Okay. So, what I want is the vertical force. So, that vertical force is T sin theta at x, actually minus, okay, with a minus. then at the right hand end the vertical force at x plus dx is again t sin theta, but this time at x plus dx. Okay. Now, what we have said here is that these angles are very, very small. These angles are very small. Okay. So that sin theta can be approximated as theta. So, if we write down the net force in the vertical direction, net force in the vertical direction, it is t sin theta at x plus dx minus t sin theta at x. Okay. And this of course is equal to the mass into acceleration of that element. Now, with this approximation over here, we write this as t at into theta at x plus dx minus t into theta at x, and that is equal to the mass, which is the density mass per unit length into the element length into the acceleration del t square. Now, theta, we have to bring theta in terms of y and x. Okay, theta in terms of y and x. So, theta is written as del y by del x. Okay, this angle is written as del y by del x. So, then what we have is t del y by del x at x plus dx minus t del y by del x at x is equal to rho L dx del 2y by del t square. And here we will use the Taylor expansion. And expanding this about x, what we have is t del y by del x at x plus t del 2y by del x square dx minus t del y by del x at x is equal to rho L dx del 2y by del t square, and that is because t is assumed constant. Okay. Now, if we cancel these common terms, what we have is t del 2y by del x square dx is equal to rho L dx del 2y by del t square. If I take out the dx, what I have is del 2y by del x square is equal to rho L by t del 2y by del t square. Okay. Rho L is mass per unit length, T is tension, which is force units. So, if you look at the units, what we will have is rho L by T will be 1 over c square, okay, where c has units of speed. Okay. So, this then becomes 1 over c square del 2y by del t square. So, that is the equation for waves on a string. Okay. And this c is the speed of the wave, speed at which the wave travels. Now, the general solution to this, this equation, general solution to del 2y by del x square 1 over c square del t square is given by y x comma t is equal to some function f x minus c t plus some other function g of x plus c t. Okay. Now, we can test this out. Okay. We will consider this one function. Okay. Let us say y x comma t is equal to f of x minus c t. We will substitute this into this equation and see if it satisfies. So, we have to take derivatives with respect to space and time. So, let us do this. Let us do del y by del x. Okay. Del y by del x is first of all derivative with respect to the whole argument, I call it f dash, then the derivative of the argument with respect to x. Okay. So, this is 1. So, I have f dash. Then del 2y by del x square, del 2y by del x square is equal to del by del x of f dash of x minus c t, and that is equal to f double dash, okay, into del by del x of x minus c t, which is again 1. So, that gives me f double dash. So, the left hand side is f double dash. Next, del y by del t is the same, the derivative of f with respect to argument first. So, f dash, then del by del t of x minus c t, which is equal to f dash into minus c. Okay. So, is equal to minus c f dash. Then del 2y by del t square is equal to del by del t of minus c f dash. C is a constant. So, what we have is minus c into del by del t of f dash, again minus c derivative f dash with respect to the argument. So, f double dash and del by del t of x minus c t, that gives me minus c into another minus c. So, minus c whole squared into f double dash. So, this side now is equal to c square f double dash divided by c square, this c square, and therefore, I get f double dash on the left and f double dash on the right. So, this form is indeed a solution. So, one can check this form also and get the same result. Okay. Now, this course is largely or mostly about harmonic excitation. Which means single frequency. Okay. Systems are excited by single frequency. That means the forcing either f sine omega t or f cosine omega t, okay, or f e to the power of j omega t and so forth, single frequency. Okay. So, now we will have to bring in this aspect of harmonic excitation into this solution over here, into this solution. That means we are going to find the form equivalent to this form when we excite the system with harmonic excitation. Now, if I have this form here, y of x comma t is equal to f of x minus c t plus g of x plus c t, okay. And then here you can see we have taken derivatives with respect to space twice and time twice, okay. Now, if I bring in a constant inside, if I bring in a constant k inside, it is not going to hamper the result, because this k also will fall out twice from both sides and get cancelled. Okay. Now, this k I am going to call it as a wave number. Significance of that we will see. So, if I open the bracket out, I get f k x minus k c t, and here g k x plus k c t, and I am going to say that this k, the wave number, times the speed c is omega, the radian frequency, the radian frequency. Okay. So, what happens here, f of k x minus omega t plus g of k x plus omega t. Okay. Now, when a system, when a linear system is excited by a force, a harmonic force, that is either f sine omega t or cos omega t, then the system responds at the same frequency. Okay. The response is at the same frequency and it is harmonic. So, the response form is going to be either a sine k x minus omega t or plus minus omega t, or cos of k x plus minus omega t. Okay. So, this sine omega t will generate a response which is a sinusoid or a cosinusoid with these arguments inside. Okay. So, So it is not any arbitrary function now, the sine here and the cosine here, they will generate responses from the linear system which are again sinusoids or cosinusoids. That means here also I will consider the exponential notation, okay, and I am used to having omega t in the front. So, I will say omega t plus minus kx. Okay. So, what have we accomplished? What we have accomplished is that our systems are going to be harmonically excited. The excitation is not going to be some general forcing of time, it is going to be a single frequency sinusoid or cosinusoid, and as a result what happens to this form is that in case of this linear system, this form will acquire a sinusoid or cosinusoid expression. And so, as we are used to an exponential notation, this is the response form. Okay. So, in the event that our system, which is a string right now, is excited by a forcing of this form, then the response will be written as sum A tilde e to the power j omega t minus kx plus B tilde e to the power j omega t plus kx. Okay. Now, we will dig a little bit more into this expression. So, how do we do that? We go and take a system. Okay, first of all, let us talk of a phasor. Let us talk of a phasor. Phasor is a rotating vector. It is a mathematical idea, okay? Rotating vector. What do we mean? If I have a vector of unit length that is rotating, okay, so the expression is going to be e to the power of j omega t. So, that if I have the real and imaginary axis, then this is equal to cosine omega t, the projection on the real side, plus j sine omega t, the projection on the imaginary axis. Okay. So, as this vector rotates, its projections will change. So, you will get both the component on the x axis and y axis simultaneously. That is why we use a complex notation. We always use a complex notation of f e to the power j omega t. Okay. The reason, one of the reasons being that simultaneously, if I want, I take the real part and I get f cos omega t, and if I want the sinusoidal part, I take the imaginary value, I get f sin omega t. So, I get a dual benefit by taking this complex notation. Okay. But that at the same time is a phasor which rotates with time, okay, and its projection constantly changes, just as cosine omega t and sine omega t, as their values change with time. Okay. And this angle is the phase angle, this angle is the phase angle, omega into t is the phase angle. Okay. So, now this is just a mathematical idea, So, by using e to the power j omega t, what I am saying is I am preserving both cosine omega t as well as sine omega t, and as and when I choose I will take the real value or imaginary value, and then I will settle with cos omega t or sine omega t. Okay. Till that point e to the power j omega t is equivalent to cosine omega t or sine omega t. Okay. So, a vibrating particle or a vibrating point will have a phasor e to the power j omega t, okay, which is composed of cosine or sine as I choose later. Okay. So, now this mathematical idea we will translate it to a physical system, which is a let us see, which is a slider crank mechanism and to this mass I have a spring attached of infinite length. Now, this, let us say this has only unit length, okay, and so now this rotates at an angular frequency omega. So, it keeps going around. It keeps going around repeatedly. Okay. So, it does f cycles per second, f rotations per second, and therefore, twice pi into f is equal to omega radians per second. Now, as this crank moves or crank rotates, it will pull this mass back and forth, okay, due to this slider, okay, and this movement of this mass will be transmitted through the spring towards the right. As this crank does repeated rotations, that information is transferred repeatedly through the spring, okay. So, there will be regions of the spring where there will be motions that are equivalent, okay. As this rotation is periodic, so is the signal on the spring periodic, okay. Every so much distance the movement is same. So, those regions where the movement is same, they are separated by a distance called lambda, where lambda is the wavelength. Okay. So, let us say we start off at this particular angle wherever we are, okay. Then this mass starts to move, and once the crank has gone around once, that information has propagated a certain distance. So, this point now carries that information, but the crank again has come back to the same point. So, this point again starts to go through the same motion. So, this point and this point have the same motion, and next time around there is another point, because by that time the signal has propagated. So, this point also has the same motion. So, there are regions where they have exactly the same motion happening because the crank is doing a periodic motion, okay. So, now the distance is lambda, which is wavelength, okay. So, now we say that these 2 points, this point and this point, they are vibrating in phase, they are vibrating in phase. Okay. So, now if I assign a phase to this crank, okay, because it rotates at omega, the phase angle is going to be omega times t. So, this angle is actually omega times t, okay, that is the phase angle phi. So, if we assign a phase to this rotation, that means we say the crank is at a certain phase, the crank is at a phase omega t. Then because this mass is hardwired, and it is doing an oscillatory motion, as we said, we can consider it as cosine if we look at it one way and sine if we look at it another way, but we will combine and look at it as e to the power j omega t. Okay. So, we can assign the same omega t phase to the first mass because it is tied to the crank. Okay. So, that we can say that the mass at this point is at a phase omega t. Let us say the crank now moves to a vertical position, then the mass moves a little to the left, and then we will say the mass is at a phase of 90 degrees and so forth. So, we can assign this phase to the mass. Okay. So, now what happens is, because there is another location on the spring to the right which is doing the same motion vibrating in phase. So, this point has the same phase, or we will say it has omega t plus twice pi phase. Okay. Because the crank went through one round during which the information got transferred here. Okay. So, now in lambda distance, the phase change is 2 pi. Okay. As the crank went through 2 pi radians, the information moved through lambda, so that these 2 points are moving in phase. So, lambda distance, the phase change is 2 pi. Okay. So, unit distance, unit distance, the phase change is going to be twice pi by lambda. So, we will give this 2 pi by lambda a symbol and call it k. K is our wave number. Okay. What is the significance now? The significance is this: as this crank rotates, with omega as the speed, rotational speed, and omega t as the phase, we can assign the same phasor to this mass over here, e to the power j omega t. Okay. And then a little distance behind, let us say delta x behind, okay, let us say we are delta x over here, okay, this is delta x, let us say. The information has not reached yet. The information that this crank is rotating has not reached here yet. So, it will get delayed a little bit. So, by how much will it get delayed? It will get delayed by e to the power j omega t minus a certain amount, okay. As you see, when a wave moves through a ocean or a lake, it moves and then it moves a little later and moves to the right a little later and moves to the right. The same information is going, but moving a little later. So, because this delta x is a little behind, it will see the information a little bit later. Okay. So, that is described by this term over here. Okay. So, this is a phase, omega t is a phase. So, this will also be a phase. Okay. And how much will it be? It will be e to the power j omega t minus the phase over delta x distance, minus the phase over delta x. Okay. But we have said that the phase change over unit distance is k, and therefore, this is going to be e to the power of j omega t, okay, minus k times delta x. Okay. So, that is the delay seen by a point delta x to the right. So, this point will see the information right away because it is hardwired to the crank. This point will see it a little delayed. If we have another mass further apart, let us say this is another delta x, then it will have a description omega t minus twice k delta x and so forth. Okay. So, if we make this phase change equal to 2 pi, okay, if I make it equal to 2 pi to the power j omega t minus 2 pi, that means there is a point to the right which is experiencing a delay of 2 pi. That means what? It is going to see the same, it is going to be the same. So, that point is in phase, this point is vibrating in phase with the first mass, and therefore, that is the wavelength. If I find a point over here, that is the wavelength, 2 points that are vibrating in phase. Okay. So, now I can make this delta x a continuous variable, so that every point has a phasor description e to the power of j omega t minus kx. Okay. Now, kx is no more increments of delta x, it is a continuous variable. So, starting with the first point, which is at x equal to 0, which is rotating along with the crank, every point to the right is delayed a little bit in receiving the information k delta x e to the power j omega t minus 2k delta x and so forth, till you reach a point which is e to the power j omega t minus 2 pi. Okay. And this point and the first point will be moving in phase, and that distance will be lambda, the wavelength. Okay. And this, the delay per unit distance, the phase delay per unit distance is k, which is the wave number, and it relates to lambda as twice pi by lambda. Okay. So, that is how wavelength and wave number are related. So, you can see that any point, the general descriptor of any point, general description of the vibration of any point at any point is e to the power of j omega t minus kx. Okay. If x is 0, you get the starting point. If x is any point, then you get the phasor description of that point. And if you want to get the real or imaginary, if you want to describe it in terms of sine or cosine, then you either take real or you take imaginary, then that way you get cos or sine, which you are familiar with. Otherwise, we keep the descriptor as e to the power j omega t minus kx. Okay. Now, I will give you the same picture in a different diagram over here. Let us say we have this as the time axis, this as the time axis. So, I will close the lecture over here. I will close the lecture over here, and we will continue with this idea in the next class. I will give you one more way of looking at it in the next class. Thank you.